Welcome back to All This Math. This is Professor Parker. And as you can see, I got my Harriet Tubman t-shirt on, where she said, "We out." Harriet Tubman, 1849. Before the Civil War kicked off, about 11 years later, 1861, I believe, right? Here's a picture of an older Harriet Tubman. You know, it's one of my favorite pictures, right? But do your research on Harriet Tubman. Definitely do your research. There's a movie about her that was made. It starred actually the late Cicely Tyson. The late Cicely Tyson actually played Harriet Tubman. I can't remember the name of the movie. I think it's like The Black Moses, or I can't remember the name. Don't get me lying. But if you do a Google search, you'll be able to find it. But definitely, you know, one of the most well-known workers on the Underground Railroad, along with people like William Still, a Union Army spy, a nurse. You know, she did a lot. She accomplished a lot. But definitely do your research on Harriet Tubman. Rest in peace to her. And again, here's the picture. All right. So we are now going to talk about some word problems. Now, the word problem is not written on the board, but the word problem is included in the description under the video. So you can you might want to pause the video and then copy the word problem down. And then follow along and then hit play and then follow along with my description. I'm going to read the word problem, of course. I'm going to read it, of course. So what we got? Okay, so this word problem, and this is like more introductory. This is like more elementary level math, which is fine, which doesn't mean that if you're not in elementary school, you shouldn't know how to do this, because you should, right? So this video is really for everybody. So let's get started. This problem says that Carlita put 63 party hats into stacks. So imagine party hats. They're like shaped like ice cream cones, basically, right? Party hats, 63 of them. So matter of fact, let's write that down, because that's pertinent information. And when we approach word problems, we either underline important information, circle important information, highlight important information, similar to when we're reading in ELA or language arts class or reading class, right? Or English literature class. You know, you highlight important information within the passage. You highlight details, you circle details, right? You put check marks over details. You draw boxes around certain important details, right? So we do the same thing with word problems. So 63 party hats. 63 party hats, right? In stacks. She stacked them up, right? Probably save space, because she don't want to just have 63 individual party hats all over the place. It's going to take up too much room. We don't got time for all that. So there are more than, then the problem proceeds to say, there are more than 5 stacks, but fewer than 10 stacks. More than 5 stacks, but fewer than 10 stacks. All the stacks have the same number of hats. Here comes the question. How many stacks could Carlita have made? How many? That's a number they're looking for. How many stacks could Carlita have made based on the information that you're given? Also, how many hats are in each of these stacks? All right. So, and of course, if you want to solve this on your own, go ahead, pause the video and go ahead and solve it on your own, and then come back, hit play, check your work, right, based upon my explanation. Now, let me go back here to the second sentence where it says there are more than 5 stacks, but fewer than 10 stacks. So if there are more than 5 stacks, I mean, it can't be 4 stacks. It can't be 3 stacks. It can't be 2. It can't be 1. It can't be none. It can't be 5, because it doesn't say 5 or more. It says more than 5. So if it's more than 5, we're talking about either 6 or 7 or 8 or 9 or 10 or 11 or 12 or 50 or 100 or a million, right? But it also says fewer than 10 stacks. So that means it can't be 11, and it can't be 10, can't be 12, can't be no number bigger than 10. And it can't be 10 either. So it's either going to be, let's write down what our options are. We could either have 6 stacks or 7 stacks or 8 stacks or 9 stacks. Now, how come we can't have 10 stacks? Because the problem says there are more than 5 stacks, but fewer than. Fewer than means less than. So fewer than 10 stacks. So that means you can't have 10 stacks, because how are you going to have 10 stacks if you have less than 10 stacks? You can't. 10 is 10. 10 is not less than 10. All right? Then it proceeds to say all the stacks have the same number of hats. The same number of hats. Now keep in mind, it's 63 hats altogether. So when you see a problem like this, automatically start thinking about factors. Factors and multiples. Factors and multiples. So ask yourself the question. If there are 63 hats altogether, if Carlita puts them in 6 stacks, then that means that each of those 6 stacks should have the same amount of hats, which means that I should be able to do 63 divided by 6, and I should be able to get a whole number with no remainder, a whole number with no remainder. And if I can do that, then that means that if I can do that, then that means that this is an option. This is a possibility. So let's see what happens when we do 63 divided by 6. 63 divided by 6 would be 10 with a remainder of 3. Because 6 times 10 is 60. So I'm going to say 10 remainder 3. So that means if she has 63 party hats and she does 6 stacks, that means she could have 10 hats in each stack. So she should have 10 in one stack, 10 in the next stack. So it's kind of like this. She got 10, and then 10, and then 10 party hats, 10, 10, 10, then 10 more, then 10 more, then 10 more, party hats. And then the last stack, she got 3. But the problem says all the stacks have the same number of hats. So that's why we got to read and comprehend first before we even start getting into the math. All the stacks have the same number of hats. Here I got 10, 10, 10, 10, 10, 10, and 3. 3 is not the same as 10. So what does that tell us? She can't have 6 stacks. So that's not an option. Cross that off. But this is one way to solve this problem. This is a process that we can go through. So we saw that it can't be 6 stacks, because if it was 6 stacks, then you would have 10 in 6 of the stacks, and then 3 in the 7th one. So we can't have that. But what about 7 stacks? If there are 7 stacks, then that means you should be able to take 63 party hats and evenly divide them between 7 stacks. So let's see what happens when we evenly divide. Let's see what happens when we do 63 divided by 7. Now, if you know your multiplication facts, then you should know your division facts, because division is just the opposite of multiplication. So 63 divided by 7 is 9. So that means that, and that's a whole number. So that means she could have 9 hats in each of these 7 stacks. So she could have 9, then 9, then 9, then 9, then 9, that's 5, then 9, then 9. So we got 1 stack, 2 stacks. These are supposed to be party hats. Another stack, another stack, another stack. 1, 2, 3, 4, 5, 6, 7. So we got all 9s. And so this follows the information given in the problem. The problem says that all the stacks have the same number of hats. So 7 stacks is cool, right? But here's another thing. In a lot of these word problems, once you find a correct answer, you would think that you're done, and then you go into the next problem. But this is not that type of problem, because we have so many options. What you want to do is you want to test each option. So then we go to 8 stacks. Let's do 63 divided by 8. Because we want to divide 63 party hats evenly between 8 different stacks. So if we do 63 divided by 8, then that's going to give us 7 with a remainder of 7. Because 56 is 8 times 7 is 56. Yeah, with a remainder of 7. So we're going to have 7 in each of the stacks, right? 63 divided by 8. 8 stacks of 7. Wait, is that correct? 8 stacks of 7. Yeah, 63 divided by 8 is going to be 7. Because 7 times 8 is 56. So 7 is 56 plus the 7 that's left over. No, that don't make sense. Let me see something. So 8, let me do some long division real quick. Why am I blanking on this? 8 goes into 63. 8 times 7 is 56. Subtract. That's 7. Yeah, 7 remainder 7. So it's going to be but why is it 7? With a remainder of 8. Let's see, that's going to be 10. Oh, you know why? Okay, that's why. Right, because, okay, I was blanking for a minute. My apologies, right? So look, because if you got 8 stacks, each of those 8 stacks is going to have 7 in them. But that's not enough. That's what I was missing. That's what I was blanking on. That's not enough stacks. You're going to have an extra stack with 7 more, right? So you're going to need more than 8 stacks, because 8 stacks is not enough stacks, because one stack would have 7, then another stack would have 7, 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 another stack has 7, another stack has 7, and then another stack has 7. Now altogether that's 56. That's 56 hats, but you need 63. So you need another stack of 7 hats, right? Which is 9, which takes us to the next option. We cross this one out. This one is 9. So we already know that this is right. You know why? Because what is 63 divided by 9? It's a whole number. 7. No remainder. No remainder. So that means we're going to have, in each of these 9 stacks, we're going to have 7 party hats. In each of the 9 stacks, we're going to have 7 party hats. So we got 7 in one stack, another 7 in another 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 stack. Let me see, how many is that? 1, 2, 3, 4, 5, 6, 7. Another 7 in another stack. And last but not least, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So we got 9 stacks. 1, 2, 3, 4, 5, 6, 7, 8, 9. And each of those stacks have 7 party hats in them. So these are your 2 correct answers. 7 stacks of 9 hats each, or 9 stacks of 7 hats each. Those are your 2 answers for this problem. All right. Now, another way, this is what I also failed to mention. Another way we know that there's going to be more than one answer, there's a hint in the wording of the problem. It says, how many hats are in those stacks? How many hats are in those? Those, that's plural. So again, I want to emphasize, whenever you're dealing with word problems, you got to bring your reading comprehension. You got to bring your reading comprehension first. Don't think, oh, this is math, so I don't got to think about reading. No, the same skills you develop in reading and in ELA, you got to bring those into math class. You got to bring those, right? And we gotta think to ourselves that we can't really do math until we know how to read and we know how to comprehend, especially when we're dealing with word problems. All right. So this was a good problem that tests our ability to do division. It tests our ability to understand multiples and factors, because 7 is a factor of 63, because 63 divided by 7 equals 9. 9 is also a factor of 63, because 63 divided by 9 is 7. 6 is not a factor of 63. That's why you can't put the same amount of hats in 6 stacks and have all 63 hats accounted for. 8 is not a factor of 63. So what this problem does is it tests your ability to understand factors and the relationships between factors and multiples. All right, in this case, 63 would be a multiple. All right, so use this video as a guide. Ask your teacher for more practice problems like this so you can develop your skills. And I'll see you in the next video. Peace.